Thank you. Morning, everyone. My name is Sanjeev. We're from Streamlio, and today we're going to present our vision towards a unified end-to-end real-time solution. So just getting started, right, and basic stuff. Why real-time? Data is coming in. The data is most actionable and most valuable when the data actually arrives. That doesn't mean data doesn't have any value later on, but the value of the data continuously keeps on decreasing. The faster you act, the nimbler you are, and therefore any kind of business decisions or operational decisions or any kind of other decisions that you want to take, the faster you are, the better. And therefore, real-time is very important. All enterprises these days are moving towards some kind of a real-time, event-driven architectures, kind of dovetails well with what we've been doing at Streamlio. How do you do this today? Well, this is the state of the art. You have some data streams coming in from the left, and this is the Lambda architecture, made famous by the company that this building belongs to, Twitter, of whom we also belong. So you have a messaging queue. So the data comes in. Data is actually split into two streams. So essentially, there's a duplication going on. One part, the top one, goes to the real-time, the speed layer, or whatever it is called, consists of a messaging queue of some sort. It could be Kafka, it could be RabbitMQ, Pulsar, DLog, and then there is some kind of a stream processing compute that happens over it. Typically, Twitter, Storm kind of started it. Twitter moved on to Heron. There is Fling, Spark, these days K-streams, and so on and so forth. Right. So a bunch of systems where you can do things like do you want to count how many tweets are you receiving, or do you want to do any kind of more difficult computations like trend analysis and so on and so forth. All of those things are modeled, quote unquote, as topologies handled by the frameworks, stream computing frameworks, and these are some of the examples. And then after you do that, you actually want to use these quote unquote results, like how many people visited my tweets, how many people retweeted my tweet, or something like that. You typically keep your result in some kind of a fast access, like a Cassandra key value store, Manhattan in Twitter's case, or Redis. Or you can actually store this in a database somewhere, for later analysis and so on and so forth. So that's the speed layer, right? And analogous, at the same time, what's happening here is that there is the data is actually copied over to long-term storage slash the batch world, typically comprised these days of HDFS as the base layer, MapReduce, more recently Spark, and so on and so forth, right? And then the reason why you sort of do that is because the speed layer is inherently lossy in some sense. It doesn't really capture accurate data. The batch layer is supposed to be accurate, and therefore you want the latest results with some data accuracy loss. At the same time, you want the result inaccuracy to be bounded, so you kind of combine it at the query layer towards the right to get the results from both the speed layer and the batch layer. And that's essentially a Lambda architecture for you, right? And from the minute you sort of see, oh my God, this is like a patchwork of systems. Like a lot of things can go wrong here. First of all, it's duplicated effort. Every data is stored at two places and acted at two places, and and the computation is expressed in two different places, and so on and so forth, right? It's actually pretty heavyweight. These days, the other flavor is the COP architecture, when you're saying, what, why are you doing everything? Everything should be done in just one, and that's real time, right? So data is coming in, you put into a message queue, and you have some kind of a streaming engine, the same streaming engines as before, and then there is a serving layer, right? What this kind of glosses over is that this is good for just real-time computation. Now, what if you actually want to do analysis over yesterday's data or last month's data, right? That's kind of glossed over. There are many ways of sort of doing that. You can say, okay, copy that data wherever you sort of kept the data in HDFS maybe to the message bus again, and then run the same topology, quote unquote, on yesterday's data as well. That's really inefficient, right? That's basically, that has very, very heavy network penalty. The other option, obviously, is that this is another kind of store, but then it kind of boils down to a kind of a Lambda architectures anyway, right? So, Kappa really, reprocessing logic kind of, fails that. And reprocessing happens all the time. And we'll show that with an example towards the end of a session of why reprocessing is very, very important. Happens pretty much every day at companies like Twitter. So, just summarizing this, patchwork of systems written at different places, maintained by different people. So you need actually a team who is well versed in each of these technologies to be actually able to just barely run. And there are too many places where things can go wrong, right? Too many failure modes. And when the APIs, when the semantics are not clear between the messaging and the compute and the storage and so on and so forth, there are a lot of losses possible that are hidden. You'll only notice once your business logic or your business results don't match the expected, what your client expects and so on and so forth. And then you'll probably be in for a nasty surprise in some sense. So what people really need here, right? I mean, at the end of the day, what people need is, data is coming in, right? They want to be able to act on the data. Data is coming in, store the data as fast as possible. There are probably a bunch of subscribers that are waiting for the data to do some action, right? So you need something which basically says, okay, there's a bunch of subscribers. I will give the data as it arrives as fast as possible in a scalable manner to all my subscribers, right? And that's usually what's called the messaging, stuff, right? And then you obviously want the data to be persistent, right? You never want to throw away your data, because your data, you will reanalyze it tomorrow, you'll reanalyze it next month, and so on and so forth. So you want a linearly, horizontally kind of scalable, durable storage, right? And this is usually, you need make sure that the data is replicated to avoid data losses. Make sure that if machines die, data is automatically replicated. All the stuff that you sort of take for granted with a distributed file system kind of thing. Obviously you want like high availability, read throughput, and so on and so forth, right? And at the end of the day, the processing is very similar. It's like a DAG. You want some way in which you can sort of express your computation as a DAG with some input source and some some DAG operators to basically operate your data on, right? Let's come to the messaging and the storage aspect of it, right? I mean, in the face of things, I can actually say, messaging and storage are probably two different things, right? In the sense that, one is actually waiting for future data, the data that will come in or it has just arrived. And it is very, very low latency. You need to be able to kind of quickly give it to the subscribers and move on, right? Storage, on the other hand, has the duopoly in the sense that, you're actually storing past data, and here the throughput, matters more than the latency. So it also seems that, they are having two different things, but the fundamental thing is that they are actually the same data. Right? The data that you come in is the same data that you're going to store in your messaging, in your storage systems. So why keep it at multiple places? Why not keep it at the same place? We will come to some of the challenges, some of the differences there, but ultimately you're dealing with the same data, right? Now, what if you've got in one system something where a very fast PubSub distributed message system, wherein the data comes in, and the data is able to be immediately sent to all the subscribers at very low latency. At the same time, the data is not thrown away, right? The data is actually backed durably by a very horizontally scalable log store. That log store that does all the stuff that you take this distributed file system for granted, right? What if you've got this in just one system, one place where the data kind of stays, right? If you've gotten that, your system, your architecture becomes inherently very, very simpler, right? You have a single place where the data resides, and therefore now you have the ability to basically store and compute on that data, whether it is today's data or yesterday's data in the same system, right? And the ramifications for the computes are even better, right? And now, since you're talking about data coming from the same system, the same stack that is actually going to work for today's data or right now's data will actually work for yesterday's data, right? One of the fundamental disconnect that is there in the market is traditional distributed file systems are not giving that benefit of low latency. They are too much into the high throughput mode, and that's the reason for all the dichotomy that sort of comes up, with multiple systems and so on and so forth. But what if you've got this? The answer is we actually have this already today, and that's Pulsar BookKeeper. And to talk about more on Pulsar and BookKeeper and why that thing makes sense, how that is architectured, I'll ask Sijie to sort of come on board.
So as what Sanjeev said is the whole point is the messaging data coming from the real time is actually became the historical data stored in the storage. So what if a system that provide single storage abstraction for both real time data and in historical data? So then you can use the same unified interface to accessing both the historical data and the real time data. So that's what we came into the picture is why Pulsar has the combination of Pulsar and BookKeeper has the value to bring in the unified messaging and storage. So to talk a bit about Pulsar, what Pulsar is. So for a simple sentence to describe what is Pulsar. Pulsar is a fast, durable, and multi-tenant pub/sub messaging. And it's open source by Yahoo last year around October. It's now in Apache Incubator for incubating. And Apache Pulsar is built in a layer architecture. What does that mean is it's comprised with, it's separated into two layers. One is serving, we call it messaging or serving. And the other layer is storage, is where data can be kept for a longer time. And this is the separation between the serving and the storage can bring in a bunch of the benefits. For example, like independent scalability. That means if you want to scaling your messaging or serving layer, you can just drop in as many as brokers in a serving layer. If you want to keep data for much longer time, you can just simply drop in as many number of bookies as the storage, and there's no need for data rebalancing. You don't need to say, I want to expand my cluster, I need to do expensive data copy. It just automatically shifting the traffic when you drop in the storage node. And because it's a steady serving, that means your messaging layer is mostly steady. The benefits of steady is when you want to shifting the traffic for online service or for any instant, you can quickly shifting the traffic between brokers without expensive copying the data. And that is the key to multiple things like multi-tenancy and low latency, I/O isolation. That is all the benefits. And if you can see here, in the layer architecture is you have two layers dealing with different aspects. Is for the serving layer, you can dealing with messaging dispatching, low latency deliver. On the storage layer, you focus on storing data for much longer time and keep the data no data loss and durable store. So underneath of the Pulsar is using BookKeeper as a scalable log storage. And BookKeeper itself is, we call it, it's a replicate log storage. And it provides a bunch of the benefits is low latency durable writes. That means by durable here is not just replication, it also means durably persist the data on disk before acknowledge. That means all the data would be on disk rather in file system memory or in cache. So this is critical for if you want to use, this is critical to a unified messaging and storage system, because if you want to keep data for much longer time, you want to make sure the data is durably stored on disk without no data loss. And it also provide a very simple repeatable read consistency. So no matter how you want to process data, you can got exactly same sequence of data. That is important for data reprocessing, because you don't want to get into a computing engine that when I process data, yesterday's data, again and again, I got different results. Then that is not good for processing engine. And it's also built in as a bunch of other features like high availability and be able to store many logs on the storage node. So it has the ability to scale the number of the logs to millions or even tens of millions. And that is critical for like things like microservice. You might have a lot of small microservice you want to consuming from a large number of the concurrent logs or topics. And also I/O isolation, that is the key to the success of multi-tenancy and also low latency. And for more information, feel up to check out the project. And because of the layer architecture, it brings a fundamental difference with other log system or like Pulsar system, is it became more segment-centric. What does that mean is segment or block is more coming from a file system or storage perspective. You break down large chunk of data into segments, and you are able to distribute all the segments across the storage node. And that is what on the right-hand side is you can see how a Pulsar topic or a Pulsar log stream can break down into small segments and distribute into storage node. And that on the left side is just show an example what is the difference with other systems like Kafka, which is partition-centric. And because of the difference of the architecture, it brings a lot of benefits in this segment-centric system. Is, for example, if you want to add more capacity, you want to expand your cluster, you can just drop in new node. Because it's segment-centric, so new data will just quickly be breaking into new segment and going to new storage node without rebalancing the partition, without expensive copy. And also, if there's any node failure, you just need to repair the broken segment. You don't need to recopy the whole partition data in order to recover. And there are also a bunch of the benefits of segment-centric architecture. Feel free to talk to me after the talk. And besides this different layer of the architecture, one thing we found interesting in Pulsar is in the messaging mode, people typically categorize the use case into two categories. One is streaming and one is queuing. This typically be done in different systems. Like for example, queuing, people might using RabbitMQ a lot in the market. For streaming, people might use Kafka a lot. But there's no fundamental difference about streaming and queuing. They are mostly for propagating all the real-time data. And Pulsar does this unification in the messaging model through a topic in subscription model. So in a given topic, you can have different type of subscription. And a subscription defines the way how you want to consuming the data. For example, on the top is exclusive. That means you can, there's only one consumer can read from one topic or one partition that is doing the sequential read and exclusive. And failover means you have multiple consumer want to consume from the same partition, but there's only one active. The other is became standby. When the consumer fail, it would just be the other consumer just take over. For people who are familiar with Kafka, the failover mode is what it's called partition rebalancing in all consumer group in Kafka. So that is for streaming. And for queuing, that is basically implemented as a shared consuming. What does that mean is if you have a given partition, in exclusive mode, you only have one consumer to consume. So how fast you can consume is limited by the consumption capability. But if you do a lot of expensive work, like for example, like video encoding, image transformation, or maybe some very expensive or complicated event processing, if you want to scale the capability, you don't care about ordering, you just need to add as many consumers as you can, because there are they are consuming, sharing, consuming from the same topic. So this is output into one messaging model. That means you don't need to distinguish like how people want to define different consumption behavior. The consumer can scale on their own way. And besides that, the Pulsar provide not just a flat topic namespace, it's more hierarchical. What does that mean is when you onboard Pulsar, you onboard as a tenant. Each tenant would have a property. And under the property, you can create multiple namespace. In namespace, you create topics. So in this way, you organize your topics in a hierarchical way. That is useful for in a company that you might have different teams. Different team might use different topic processing, different business logic. So in this way, you can segment, organize your topics, and you can grant the some kind access control. So for people, they might only care some of the topics. So critical data, they are not be visible to other people. So that is the way for people to achieve multi-tenancy. And besides that, the other important things for messaging system is you should have capability to replicate data between data center for data center disaster recovery. So this is done in Pulsar in a very nice way. It's built in the messaging layer, which is in the broker. So when you want to enable geo-replication or cross data center replication, you just config for a given topic which cluster or which data center you want to replicate to. You don't need to set up additional complicated maker to run as an additional job. What does that mean to a lot of use cases is if you have a lot of data center, that will simplify your management. If you are running in IoT area, you might want to do edge to cloud replication, and it's so hard to managing a lot of edges if you using additional job. So this geo-replication facility bring in a lot of value to simplify your architecture. And Pulsar provide a lot of client library like Java, C++, Python, and WebSocket for people to access. And it also supports partition topics, so you can still scale the topic with increasing the number of partitions. And it also, for people who want to are familiar with Kafka, it also provides a backward compatible API for accessing the data. So it's just additional to existing Pulsar library. And it also does a bunch of things like transparent batching, compression, TLS encryption, and authentication. And the other thing I want to call out here is it also provides end-to-end encryption. What does that mean is for a given producer, you have the ability to encrypt data before you send it to the broker. And broker should, the storage system should start this encrypt the message transparently, so they don't know how to decrypt. And only consumer be able to decrypt the system. So that is important for a lot of use cases that require a high security demand. And that is an overview about how Pulsar and also the BookKeeper looks like, and what is the idea around unification of messaging and storage. And I hand to Sanjeev talk about compute side.
Thanks, Sijie. So Heron incidentally was built right here at Twitter, and I'll just quickly go over this and probably try to spend more time in the examples because that's where this thing hopefully will become more concrete. It's just a processing DAG, right? So directly a cyclic graph, and a bunch of sources, you can do a bunch of transformations and so on and so forth. Much of you guys are already familiar with the concept of sort of a processing DAG, right? Now, one of the key things is that Heron is actually just a library. It's not a system. So there is no Heron cluster running everywhere, right? One of the key decisions we sort of made when we were sort of designing Heron was that, nobody wants to maintain another Nimbus equivalent, right? It's too complicated, There's already one that people are already maintaining, and that's the scheduler, right? Whether it's Kubernetes, Mesos, Yarn, or whatever, most people, and increasingly even mid and small size companies, are also having, a scheduler of their own, increasingly Kubernetes. So what that means is that the scheduler is the one that actually kind of manages your resources and makes sure that, things are allocated to the right ones appropriately, and if things go bad, kind of restarts them and so on and so forth. So all that logic kind of thing that was there in the Storm kind of went away. All that thing went away when you sort of dealt with designed Heron. So Heron is just a library. So you submit your topology, and the topology will essentially act as a job running inside a scheduler. So imagine if you're running it as a Mesos in the Mesos scheduler, it's just a regular Mesos job. It has a bunch of containers inside the job, but at the end of the day, from a scheduler perspective, it's just a job, right? And that's one of the reasons why there is no system to maintain, and that also makes the thing very scalable, right? There is no single point of failure or single point of bottleneck for a Heron topology. All of the topologies are acting as independent jobs working of their own. One of the main things we want to do is task isolation, right? Doing disparate things in multiple threads in a single process sounds good at the beginning, but when you are really dealing with high throughput data and so on and so forth, it's just a bad idea. And these days, with processing power and memory being so cheap, it actually makes sense to forgo a little bit more in terms of memory and actually go for task isolation as in all the tasks running as individual processes, right? So if you look at a particular Heron topology, in this case there are like 3 containers for this particular topology. Each of these data containers, the instances I1, I2, they're actually running as processes, and these could be your sources, your sinks, your transformation bolts, and so on and so forth. And in addition, there are a bunch of other tasks running. What this actually means is that all of the tasks are isolated by their own, and they actually have process level isolation, not just thread level isolation, which means that they can actually be more minutely controlled, more minutely troubleshoot, right? And the other thing is that these instances are written in their native language. So Heron actually supports a bunch of languages, C++, Java, and Python. So when you're running a Java topology, there is only Java in your stack. There is no JNI happening anywhere in the thing. So when you actually get an exception, it's a pure Java stack. It's a pure Java thing, rather than a mumbo jumbo of different layered stack, different languages. It actually makes developer productivity increase tremendously, because now you're dealing with a particular language, a runtime environment, which a developer is probably very well versed with, right? So if you're running a Python topology, for instance, the instances are all Python processes rather than any kind of things just invoking Java and so on and so forth. This means that any kind of Python processing, any kind of Python developers who's familiar with the Python debugging tools and so on and so forth can now attach the debugging tools right into each of those instances and can debug them as if he or she were doing regular Python development. The other interesting thing is the backpressure aware. We don't drop tuples. So in a processing DAG, some nodes are fast, some nodes are not fast, some processing logic is inherently expensive, and if particular downstream components are not able to keep up, you have the ability of saying to the source, we cannot consume. Let's stop consume for a while until the traffic kind of clears up at the downstream components. And once you sort of have the clear up component, you can then start consume again. This essentially means there are less data losses in the system, and this actually has resulted in a tremendously improved latency and accuracy as well. And usual, you have multiple layers. You have the old Storm compatibility layer, where if you have a Storm topology, people can actually program in spouts and bolts and so on and so forth, which gives a little more control, but probably a little more verbose to program. You also have the Streamlit API, which is more functional. So you have your flat map kind of equivalent, and SQL is in the works. So you also will have a declarative way of expressing your computation and so on and so forth. So multiple different ways of computing the same things are available. And here is where I want to hopefully spend a little more time. Just take a very simple use case, right? You've analyzed your data, you've created a classification model, and what you want to do is, as soon as a tweet sort of comes in, you want to classify it in some sense using that model. And once you sort of classify that, you want to be able to sort of add additional attributes to the to that particular tweet, and so on and so forth, right? This can easily be constructed as a real-time topology, right? Now, what's actually happening is that when your real-time topology is running, this is how typically it is actually, running. You have SPOW, you have the sources. You have the source is a tweet stream. Let's just say it has 2 partitions in this case, and your real-time job is actually processing those incoming tuples. So here is 2 source instances, each acting on partition 1 and partition 2, and they're actually processing of offset there, right? This is a very standard way of doing a real-time computation job. Nothing special here, right? This is how real-time computation actually works. But, and here's the interesting thing, right? Frequently, usually almost always, what happens is that tomorrow you have a better classification model, right? Now you've ran some more data, and this classification model you think has more models, more classifiers, and is in general a better accuracy in whatever regards you want. Now, in addition to actually classifying your tomorrow's incoming tweets with the new classification model, you actually want to classify yesterday's tweets as well, or for that matter, last month's tweets as well, because you want to be able to, now that you have a better model, you want to be able to classify all your tweets and have some kind of a histogram or whatever it is that you want to do, right? Without the unification strategy, how would you do this? It's actually very cumbersome, right? And if you were in the Lambda architecture, what you would actually do is that you would go write a Spark job or a MapReduce or have a higher level like Hummingbird run those things for you, right? So those programs are now running in a different stack, and because they're running in different stacks, there's a lot of tuning and so on and so forth to be sort of made and so on and so forth, right? With the Kappa architecture, what you need to do is that you need to bring back yesterday's tweets or last month's tweets back into your messaging pipeline and then run the topology as it is, right? In either case, very cumbersome, either network or developer productivity really hurts with it. With unification, right, we sort of said how distributed log, how Pulsar and BookKeeper kind of unified that storage and messaging layer. You don't need to do actually anything, right? These were your partitions of the tweets, and they actually were naturally stored as segments, and all of them were available at BookKeeper already. So all you need to do is that when you start your job reprocessing yesterday's tweets, you just have to choose a different offset. And that's about it. The system does not have any other limitations besides that. You just start the processing of that. And so reprocessing now is very simple. It's just relaunching that job with a different offset, and things automatically sort of get sort of taken care of by you, right? That's just one example of how reprocessing with the unified architecture kind of makes certain things which had a lot of high friction very straightforward. Unfortunately, we are kind of out of time. If you want to learn more, obviously there's a lot of blogs and other stuff on our website, as well as in each of these project websites. So feel free to go and browse. Any questions? We'd love to take either now or later. Yeah, Oscar. Yeah.
This is just amazing, incredible work. Good work, Sanjeev. Really excited to see it. So, just to be clear, I wasn't being facetious. I used to work with Sijie. She's a great engineer. I was just joking around, so that was no intent to be facetious. As you know, like Twitter, we've experimented in the past. Well, they have. So say we with this kind of Lambda style approach. Now, a lot of people say that that's maybe not such a great idea, like in the long run. And I think you're talking about at the end there, this notion of like you could just like you want to rerun the job, start with the offsets. But what's the story for like machine learning? We often want to go back and do like backfills, and some companies, unlike Twitter, have small enough data that they can actually go back and redo backfills all the time. And I don't really know of anyone operating, and I don't know enough about BookKeeper, I don't know of anyone operating Kafka in a way such that they have, just like, 10 years worth of data in a Kafka queue that they could just go point the job back, arbitrarily back. So is that a vision that you see, like with Streamlio, like you just like kind of go point it all the way back, and can you do that with BookKeeper? And kind of what are your thoughts about the long term, like bringing transactional kind of like, just run it correct the first time on streaming, because it actually doesn't have a fire hose of data shooting at it, and you can actually do it. Is that like the way forward?
That's essentially our vision, right? So a couple of points that you raised, right? Like, nobody is doing that with Kafka of actually pointing it to last year's worth of data and running it, because by definition, remember, the Kafka partitions are limited by the disk capacity on one particular broker, which means that they have a certain finite size. Now, because BookKeeper and Pulsar breaks a partition into segments, and these segments are then distributed across your cluster, there is no real limit to the size, the length at which a particular partition can grow, right? Which means that you can keep a very long partition that spans across an entire year, for instance, right? All of that now makes exactly what you said possible, wherein you just point out to the right offset, and the same thing basically runs. That's exactly our vision, and that's only possible if you have a segment architecture, segmented way of architecturing a partition rather than just a partition-centric architecture. You hit it right. That, I think, is what increasingly people will start doing.
All right, and I think we've got to stop there so we can move on to the next talk. Let's just say
Thank you.
again, Sanjeev.
Thank you.